In part 5 of this discussion, I want to talk about steep slopes, landslides and rockfall, saltwater intrusion, and wildfire hazards. Steep slopes, landslides, and rockfall hazards are associated with areas that have steep slopes and underlying soil and geologic material that's unstable and causes landslides and slope failures in the landscape. We can talk about a couple of different kinds of land failures. First is what we call a rotational slide in soil, where literally a soil mass essentially breaks away and rolls down the slope. In other words, it kind of slides down and rolls across the landscape. This is in contrast with what's called a planar slide in the bedrock, where two geologic planes that meet one another, the formation slides down slope across that plane. So we can talk about rotational slides and planar slides. The planar slides tend to be more characteristic of areas that have strong edges or surfaces in between one geologic formation and another geologic formation. The rotational slides tend to be more characteristic of unconsolidated material. We can see in the diagram on the lower right-hand corner a rotational slide where the slope has failed a couple of times and debris then is sliding down across the adjacent landscape. We can see a situation here where we have a rock slide immediately adjacent and exposing material in the face of the slide itself. Here we can see a rotational slide of a mountainside that has slid down into an adjacent neighborhood. Now, one has a hard time predicting these kinds of characteristics, but with the assistance of geological investigations, we can begin to get some sense of the probability of slope failure given underlying soil characteristics and underlying geologic characteristics and existing surface activity. In the lower the lower right-hand corner, we see an image of a rock slide, a rockfall area out in the Colorado Rockies, where a significant rock formation has broken away from its surface and crashed down the slope across a highway. Not too long ago, well, now about 10 years ago, in Ozo, Washington, there was a significant landslide, a rotational slide. The diagram in the upper left shows what the original landscape looked like, and it shows the areas that are labeled landslide with a red arrow in them, wherein the rotational slide occurred. And in the upper right-hand diagram, we can see the scarp created as that rotational slide moved down the slope. In this situation, we can see that the landslide was quite significant. A significant portion of the mountainside rotated and slid down the mountain. And it not only caused destruction of the material in the landscape immediately downslope from the slide itself, but it sent material across an adjacent river and created a dam on that river. So it opened up, it created a new reservoir behind the landscape. So not only did we have damage associated with the landslide itself, immediate damage associated with the landslide, any structure or vegetation in the immediate vicinity of the landslide was destroyed. We also had the landslide debris flowing across the landscape, but we also had significant flood damage associated with the creation of the reservoir, the upstream from the landslide itself. Here you can see damage associated with the Ozo, Washington landslide. And you can see significant amount of the adjacent landscape is now underwater. some of the structural damage you can see in the lower diagrams, and you can see the escarpment created by the rotational slide as the hillside broke away from its underburden. We can begin to do some modeling, some identification of where we might find in the landscape these kinds of hazardous conditions. We might begin to prospect on the likelihood of steep slopes, landslides, and rockfall hazards based upon steepness of the slope. Obviously, the steeper the slope, the higher the probability of failure. Composition of the underlying bedrock, consolidated bedrock, has the lowest probability of failure. Fractured bedrock and rock rubble have intermediate levels of hazard risk, and those areas that consist of compact clay and loose wet clay, these clays are very, very slippery, and they tend to result in overburden literally sliding off of the loose wet clay underneath. So based upon composition, if we have an underburden that is consolidated bedrock versus an underburden that is compact or especially loose and wet clay, we can see that there is a greater risk of landslides occurring in the loose wet clay area than in the consolidated bedrock formation. Also, the history of landslide and slope failure, where we've had no past failures, likelihood of new failures is less, whereas where we've had recent failures within the 19th or 20th century or fresh failures in the latter part of the 20th century, we can expect the possibility of future slides being higher. Vegetative cover influences the prospect of landslide, as tree roots have a habit, plant material has a habit of stabilizing surface overburden, whereas areas that don't have extensive forest cover have a higher possibility of failure. Where we have a lot of subsurface drainage, seepage of water, especially if it's combined with clay soils, we can see seepage landscapes, especially in clay areas, having strong slope failure possibilities. Also, land use activity, where we have totally undeveloped slopes, the likelihood of slope failure is less than in situations where the slope is completely developed, because there's an inordinate amount of force being exerted on the slope itself. Here we can see a map of incidents of landslides in the state of Washington. Again, these maps can be generated at the state level, they can be generated at the county level, they can be generated at the municipality level, again, with careful guidance from geologists, so we can begin to identify where in the landscape we're likely to find these types of slope hazards. This is a map in West Virginia, in a town that I once lived in, Clarksburg, West Virginia. And here we're mapping steep slopes, then indicative of areas that have higher possibility of landslide. This is Boulder County, Colorado, in which geologic hazards are mapped on a number of different cases. The pink areas represent major extensive problems. The yellow areas are moderate problems, and these are areas of potential failure needing intensive geotechnical and geologic investigation. We can also talk about hazard assessment and mitigation associated with saltwater intrusion into coastal groundwater resources. The situation here is a situation along a coastal region wherein we have a land surface that has freshwater underneath of it, a freshwater aquifer, immediately adjacent to saltwater that is associated with an adjacent saltwater body, usually some part of the ocean or saltwater, a bay, etc. If we sink wells into the freshwater, as we have in the middle diagram on the right-hand side, if we sink wells into the freshwater and start pumping and overdraw the well water from the freshwater, we will actually begin to cause saltwater intrusion into the freshwater aquifer, resulting in contamination of the freshwater well by saltwater intrusion. We see that in the lower left-hand diagram, where the freshwater well was sunk into the aquifer, the underlying aquifer. The aquifer was pumped for a long period of time, and it began to draw the salt water from the ocean into the freshwater well. There are possibilities for mitigating this in the context of injection wells. We see in the lower diagram on the right a seawater barrier injection well. And the idea behind this is that in the incidents where we have a pumping well that's drawing increased intrusion of salt water into the freshwater aquifer, if we create an injection well between the pumping well and the source of the salt water, we can actually begin to push against freshwater against the salt water, causing the intrusion to decline, to be minimized. Finally, I want to talk about wildfire hazards. Information about land cover, water resources, weather, and development patterns help us assess wildfire hazards. Things that we need to be considered, you can see, are posted here. Vegetation, topography, what's the prevailing wind effect, what is the effect of large bodies of water on creating lake shadow effects, what kind of access exists into and out of the site, what kind of available fire protection exists, placement of utilities, proximity to managed natural areas and vegetation. These are a number of different considerations that need to be thought about in terms of trying to identify, map wildfire hazard zones and talk about mitigation of these hazards over time. Wildfire hazards can affect personal property and public infrastructure. Development decisions and climate change increase these risks. Mitigation can be accomplished through site design as well as through more regionalized landscape planning. Here in Napa County, California, you can see a wildfire hazard map showing the fire risk of different landscapes within the Napa County area, basically a fire risk map. So in this context, then we could begin to talk about, well, where does it make sense to expand new development? And certainly the areas that are red, and particularly red areas and the orange areas, are less desirable than the areas that have low fire risk mapped in yellow. Finally, in part 6, I want to talk about natural and cultural hazards in the Lake Township study area. These are hazards that you're going to be mapping in an exercise in class, and they have to do with two different kinds of natural hazards, potential flood hazard and steep slope hazards, and cultural hazards, hazards associated with potential noise sources. Flood hazard is essentially a process of identifying the FEMA 100-year flood zones within the landscape and identifying the hazard rating of these different flood zones. So you'll be mapping potential flood hazards based upon FEMA data for flood hazards in the study area. You'll also be looking at steep slopes to identify those areas that have highest possibility of slope failure. And you can see that in the southeastern corner of the study area, there are a series of steep slopes that are associated with a bluff that goes along the Minnesota River Valley. And these slopes then have much higher prospect of failure than the rest of the study area. We can also talk about noise hazards and talk about noise hazards associated principally with road traffic. And so Highway 312 and 212, which are the principal major highways running through the landscape, have the highest noise hazard. The other highways have lower levels of use intensity and consequently have lower levels of noise hazard. So you'll be mapping the flood hazard areas, you'll be mapping steep slope areas, and you'll be mapping noise hazards associated with transportation. Thank you very much.